Okay, so chapter 18 in OpenStax takes us into the beginnings of the cardiovascular system. And the first item of interest along our journey is going to be blood. We know that blood is, or maybe you recall, maybe you've forgotten, it's been a while since we've done tissues, but you'll remember that blood is a tissue, it's a connective tissue. And the definition, remember too, or recall of connective tissue is going to be cells in some sort of matrix. So we are going to see cells in a matrix. Okay, that's really kind of the name of the game with this particular system. All of you have seen blood, I'm sure, have heard of blood. Some of you may be phlebotomists or have phlebotomy training. If you don't have phlebotomy training right now, and all of you are going to go into nursing, that's something you may want to think about doing. If cardiovascular and blood is even of somewhat of an interest to you, phlebotomy training and certification is relatively quick. It's a matter of performing. You attend a few kind of face to face, well, now probably Zoom type seminars, maybe face to face, and then you do a series of practice kind of blood draws, and you basically gain hours or gain experience doing that, and then you take a test and you're a certified phlebotomist. So that's something that you may want to add to your toolbox as you go. So anyway, there are always a need for phlebotomists. And again, if you're going into nursing, you might as well have that as well. Looks good on your resume as you guys start going into to applying and going through the system. So anyway, we start with blood. When we look at blood, we're going to see, again, tons of different types of cells. We're going to see primarily red blood cells. I think, again, most of you have probably heard some of these terms. We're going to give them a little more of a sciencey spin, but we do see red blood cells. We're going to see white blood cells, and we're going to be seeing something called platelets. So those are the three primary cell types that we'll see. And then all of the rest of the material on a cellular level or on a solid level that's contained within blood would be other items outside of maybe those cell types. So we would find some nutrients, some groceries, right? The blood transports, the plasma primarily is transporting a lot of amino acids and carbohydrates or simple sugars. We're transporting a lot of lipids and fatty acids. So blood in general is more than just the cells that are contained within it. There's a lot more going on, as you guys probably know. We see the terms antibodies, right? Especially nowadays, we're constantly hearing about antibodies and how they affect our health. So we'll discuss a little bit with antibodies. Just briefly today, the last section of this Unit 8 is going to be on immunity and the lymphatic system. So in a couple of weeks, we'll dive a little bit deeper into what's going on with antibodies and antigens. But we'll discuss it a little bit coming up here in a few minutes. So, oh man, what else? There's all kinds of stuff, right? Groceries in the blood, vitamins and minerals certainly are being transported. We've got hormones, right, being transported in the bloodstream. So, all kinds of awesome items that we're going to find. We also find some not so awesome items. We're going to find some garbage, right? We're going to find some cellular waste, cellular debris. You may find the remnants of cells that have been destroyed. We may find remnants of viruses or bacteria that have been destroyed. That's good. We hope we find the remnants, and then the body is going to remove or eliminate those waste products. So the blood, really, on a functional level, is transporting nutrients. It's also transporting and delivering for elimination waste products. So this is kind of the super highway of transport to our cells for chemical transport. Again, we break everything all the way down to that chemical level, and how do we get these big macromolecules, these usable nutrients, carbs, proteins, and fats? How do we get these vitamins and minerals? How do we get these gases, right? How do we get oxygen delivered to the cells? So again, ultimately, the organelles of the cells, our mitochondria, our Golgi apparatus, along with the rough endoplasmic reticulum, smooth endoplasmic reticulum, the ribosomes, all of these little items we talked about way back at the beginning of the semester inside of a cell are going to be using the items that the blood is delivering to the tissues and to the cells. So again, blood flow is extremely important. So obviously, blood content, right? What's in the blood is important. We do a lot of diagnostic testing and analysis of blood samples. So what's in the blood, and then from there we're looking at where is it going, what is it doing, how well is it traveling, how well is it able to get to where it needs to go, or how well is it able to leave where it needs to go. So we go a little bit further into talking about blood pressure and the arteries and the veins and some of the vascular aspects of the cardiovascular system. So we start with blood. We start with the main kind of connective tissue and main component of the cardiovascular system that's being transported throughout the body. And then we'll segue into the cardio part and talking about the pump that actually gets this blood moving throughout the body. And then we'll get into the vascular part, the blood vessels. So and blood pressure a little bit, and so anyway, primarily, again, we're looking at the components of blood and kind of why do we have it? What are the functions? Again, transportation and delivery of nutrients, elimination, transport toward elimination of waste products. We're also going to see some pH aspects play a role regarding systemic acid-base balance, and how, again, how well the blood is able to flow and transport wastes such as carbon dioxide, primarily carbon dioxide. So as a waste gas. Um, so anyway, it's also it's there's a lot of water, plasma, the main kind of matrix or component of the that part of the connective tissue aspect. Within that matrix or that plasma, again, we're going to see primarily water. So blood is certainly going to be helpful when it comes to hydration mechanisms. So anyway, those are the main components of blood. When we look at this a little bit closer and kind of break down the percentages a little bit more, we do see what's called, again, plasma. We see looks like a little over half of your blood. So I would say around normal, around 55% of your blood volume should primarily be plasma. Okay, so 55% of your blood is plasma. Okay, and we'll talk about what are the ingredients of plasma, what is plasma in just a few minutes. But it's the liquid, primarily liquid matrix of blood that the cells are contained within. Okay. And it's mostly water, but we do find again a lot of those nutrients that get delivered, a lot of the waste that gets removed, a lot of that solid stuff, those microparticles. We're going to again see hormones. Those are all going to be transported by the bloodstream and certainly found within the plasma portion. By the way, this illustration is certainly not what blood looks like, right? We don't take blood and it just divides like this. These test tubes were centrifuged, meaning they were spun really fast in a circle in order to get the solids or the cellular aspects separated from the liquid aspects. We're going to go ahead and centrifuge the blood samples. Okay, so that's what's going on here. That's why the blood is separated. Now, it's kind of like your uh, Italian dressing, right? In your fridge, it sits for a while, and all of that garlic and onions and pepper and everything kind of separates at the bottom. And then at the top, you've got the oil, the more liquidy portion. It's called a colloidal suspension. It's basically like a solution, right? You've got solids contained within liquid. In essence, it's a solution, but they call it specifically a colloidal suspension. We'll look at that in more detail next semester when we go a little bit further with some of the physiological aspects of blood. Okay. So anyway, plasma, 55% primarily made of water. And then we're going to see what's called a buffy coat, kind of in the middle between the plasma and then that bottom red portion. So we're going to skip the buffy coat for now. We're going to come back to it in just a second. We're going to go all the way down to what they call the hematocrit, or the kind of the packed cell volume. So hematocrit's primarily going to be made up of red blood cells. So whenever we see hema or hemato in a term, or whether it's contained within it or in front of it, like hemophilia, hematocrit, those are two that you may have heard of before. Hemoglobin. Heme actually means iron, and typically we would think of heme also meaning blood. Maybe more specifically, though, it means iron. Then kind of breaking it down from being blood, heme, to being iron. And then in the middle, we generally would think of red blood cells. So oftentimes hemato has to do with blood, red blood cells, and more even specifically iron. So that's what we have here. We can generally, the red blood cell volume, or the hematocrit, should be around 45. If plasma is about 55% of the blood volume, we typically see red blood cells making up the rest. So what that tells us is the white blood cell platelet aspects are very minimal. Less than 1% of your total blood volume will be those other two. So we'll look at that in more detail coming up. I've got a few images and illustrations and tables that detail that a little bit better. Okay, so hematocrit, that's going to be the percentage of red blood cells. This is a clinical test that we do when we do a complete blood count. We want to know what the individual's hematocrit is. A normal hematocrit should be right around 45, okay, 45%. Now, for females, it can be a little bit lower and still be in the normal range, 37 to 47%. So again, there's going to be a range for normal hematocrit. Now, if you're at the high end of that range or the low end of that range, so if you're at a 47 or a 37 or 38, that could kind of sound some alarm bells, but not extreme, but it's something we would definitely take note of. I mean, we're doing a CBC, a complete blood count, for some reason to begin with. We don't just do them on every patient that walks in the room. So the fact that we're even doing one on somebody is an indicator that maybe something's wrong. So if we do see that they're borderline, they're still in normal range, but they're borderline one way or another, we definitely keep that in mind. For males, the hematocrit can be the range is a little bit higher. So if a male came in and we did a CBC and they had a 37 hematocrit, that's abnormal. That's out of the range. Okay, so whereas for a female, 37 is still technically within that normal range. If a female, likewise at the other end of it, if a female came in and we did a CBC and her hematocrit came back as being like a 48 or 49, that would be abnormal. There'd be some red flags for sure. Whereas for a male, at 48 or 49 may be, yeah, that's in the normal range. So we So anyway, keep that in mind as well for hematocrit. Why is that important? Why is red blood cell count? That's basically what we're looking at, right? Red blood cell percentage or red blood cell volume. Why is that important? Well, we'd have to look at what the function of a red blood cell is, and which we'll look at in more detail here in a few minutes. But just kind of as a teaser trailer, red blood cells carry oxygen. So remember, going all the way back to cells and mitochondria, and what we talked with cellular respiration or ATP, energy production. Okay. Again, that's a lot of functional stuff. It's a lot of physiology. We do that next semester in more detail. But again, I think at this point, if you hear the word mitochondria, you definitely need to be connecting that with energy production or energy in the form of ATP. Yeah, it's not really energy production. It's energy exchange. Okay? Energy is not really created or produced per se. Okay? But anyway, mitochondria are responsible for ATP, which is cellular energy. And what's the recipe for ATP? Ideally, we're going to get oxygen and glucose. So red blood cells provides our mitochondria with oxygen. Okay? And then that oxygen, again, we can convert that into ATP or energy, okay, along with glucose. If we have a patient who's showing and expressing extreme lethargy or low energy, normally they're not. Normally they're pretty vibrant. They have a lot of energy, and then suddenly they're kind of hitting the wall. But they're not recovering. It's becoming a chronic issue with this individual. So that's not normal. Let's run some blood tests. We come back, we see that maybe they have a low hematocrit number. It's a female. We run a CBC. We find her hematocrit is like 27. Okay, so low amount of red blood cells. That means we don't have as many carriers of oxygen that we normally would have and normally would need. So the fact that this individual is tired all the time and has no energy, okay, those are key terms we're looking at and listening for when our patients come in. Okay. Oh, I'm tired all the time. I have no energy to do anything. Bing, you're thinking vroom, all the way to the cellular level, ATP, mitochondria, okay, glucose, oxygen. This individual might just have some problems with supplying mitochondria with glucose and oxygen. All right, so let's find out. Maybe they've got some diabetes issues. They've got low levels of insulin. So we're unable to deliver glucose to the cells. Maybe they've got some red bloods. Maybe they're anemic. They've got low numbers of red blood cells, so they can't carry as much oxygen as they need. So when you're working in the medical world, you're like a detective at the very least. All right. So anyway, anemia, we see that depressed hematocrit percentage, that it's going to lead to certainly some lethargy, a lethargic patient, and someone who's tired. Yeah, we could run the tests and everything looks normal, right? So we could go further. Maybe we could start looking at insulin levels. We could, so maybe that's why they're sluggish. Maybe there is a whole slew of other issues, but that's one thing we see, and we do see anemia generally is more common in female population than male population. There are multiple different types of anemia, by the way, too. I minimally 6 or 7. Okay, so just depends. You maybe heard of sickle cell. That's a type of anemia as well. So that deals more with genetics and heredity. Okay, anemia can be environmental as well. So let's see. That's the hematocrit. That's red blood cells. So we'll look at a little bit more detail of red blood cells here in just a few minutes. And then that buffy coat, that little coat there in the middle, that's going to be white blood cells and platelets. And again, both of those are less than 1% of the total blood volume unless there's a problem, right? So again, if we've got issues with a patient and we run a CBC, we can maybe also find out what their white blood cell count is. So we just did red blood cell count. Now we can also look at white blood cell count. And white blood cells, you probably all know, relate to the immune system in some way. So if there is an infection or if there is some sort of inflammatory issue, we may a parasitic infection too. There's a specific white blood cell that is shows up extremely high if there's some sort of tapeworm or intestinal parasite. So, but anyway, most of the time we're thinking of some of the most basic immune system functions regarding an infection from a pathogen like bacteria or virus. But white blood cells help with other types of immunity breakdowns or immunity issues. So, uh, so anyway, platelets, we'll talk about white blood cells more. There are 5 types of white blood cells. So we'll see those shortly. And then platelets is the next cellular item within blood. We would see platelets involved with blood clotting. So again, they're always around. They're the smallest of all of the cells of blood. The platelets are the smallest. They're always around. They're in very small amounts or small I guess, in total percentage of volume because they are so tiny. But we do see a lot of platelets generally in the bloodstream. They're there, but they're so tiny you don't pick them up that much, and they don't take up a lot of space. So, but they're basically on call at all times if we have some sort of a breach in a blood vessel. So these guys help with blood clotting. So we'll see the sciencey word for all 3 of these cells: red blood cells, white blood cells, and platelets, in just a few minutes, and we'll go into a little more detail. The other thing, so if I have something like this where I've got too many red blood cells, one thing we're concerned about is they blood volume may be fine, so they may have the right number of red blood cells. They may be lacking plasma. So we could have a hydration or a plasma problem over here. So if I increase plasma, that that will cause that will alter the percentages. So right now I may be looking at like a 70-30 red blood cells versus plasma. Well, if I increase the amount of plasma in the blood, but I don't increase the amount of red blood cells, eventually the plasma percentage will increase. So anyway, this could be a sign of extreme dehydration. Um, the other thing we could see with excess amount of red, where are blood cells produced, right? Red blood cells, we know, are produced in bone marrow, right? Going back to red bone marrow specifically. So excess amounts of a polycythemia issue could relate to some sort of bone marrow issue. So we could have an indicator of hyper production of red blood cells. So we could have a hyper amount of specific types of stem cells within the bone marrow they're too many. So we could have like bone marrow cancer, and that's bad. That's a tough one to treat, and the prognosis is usually not very good. So we'd never want to see something like this on the right side. We like to see everything right over here. And that's why, again, there is a range that's acceptable. All right, so let's look at plasma in a little bit more detail. Um, so again, roughly 45% or roughly 55% of your blood is plasma. Okay, 55%. So we do have a range again that's acceptable, because again, if we have hematocrit ranges that are acceptable, then the plasma ranges would shift concurrently with the red blood cell volume or the hematocrit. Okay. Oh, the other thing I wanted to mention real quick, and we'll see it shortly, but hemoglobin is another item we associate with red blood cells. So keep that in mind, because we can also do a hemoglobin number test. So hematocrit doesn't necessarily mean this is the amount of hemoglobin we have. Hematocrit is a percentage of red blood cells relative to the rest of the blood, primarily plasma. So what's the percentage of red blood cells versus the percentage of plasma? Okay, hematocrit percentage of is a percentage of, so that's a part of a whole. Okay, whereas hemoglobin count actually can go deeper and look at how much hemoglobin, not in a percentage, but in an actual number of an amount. So that comes into play, especially if we see something like this on the right side, or either one of these. If we see a bad hematocrit, we can say, well, let's look at the hemoglobin levels to find out if the hemoglobin levels are also going to be low or high. So if we have an anemia situation like this one in the middle that shows hematocrit or percentage of red blood cells being low, that could also mean, oftentimes it does, that the number and amount of hemoglobin is also low. That's typically the case, but not always. We could just have an excess amount of fluid. So if I have way too much plasma, the percentage of red blood cells relative to the amount of total blood volume is going to be low. So I wouldn't see an increase in hemoglobin. So the hemoglobin levels might be normal. I know we're getting into some math on a Tuesday morning and some statistics and percentages and stuff, but I hope that kind of makes sense. Remember, percentage is just a kind of like it's a comparison. It's a part to the whole. It's a ratio, right? That's a percentage. So we're comparing red blood cell amount to plasma amount, and then we divide, and that's our percentage. So again, usually if that number's low, red blood cell number, hematocrit low, usually we see hemoglobin low, because where is hemoglobin? It's inside of red blood cells. So again, most of the time, I don't know about most, often the hematocrit is low, the hemoglobin is going to be low. Okay. But if if blood volume has increased for some reason, plasma volume has increased for some reason, red blood cell count stays the same, hemoglobin count stays the same, but the percentage of this amount is decreasing because we're increasing the other part. So again, keep that in mind when you're looking at CBC readouts. I'll pull one up on Thursday, a complete blood, like a sample complete blood count reading. Once we go through all of the basic structures of blood, Thursday we'll look at, all right, what's a clinical readout look like with each of these numbers, and can we determine, is this patient normal, abnormal, what's going on? So again, hemoglobin count and hematocrit are separate, even though they both are analyzing red blood cells. All right, so we'll keep going. And again, as you go on in this field, and you go on in our program, you'll be doing a lot of more analysis of how these items we discuss in general A&P and advanced A&P, how they relate on a clinical level. I discuss them now because once you get into your clinical type courses, you're not going to be completely blindsided by why we even concern ourselves with the anatomy of blood. Okay? I mean, blood's a big deal, right? In the clinic. So, because it tells us a story, it tells us, I mean, look at all the stuff that could be in plasma. All right, so plasma, back to our components and percentages. Plasma, again, you're thinking roughly 55%. So now we're looking at 100% of plasma is going to be 92% water. So most of the components of plasma is water. Okay, so water is so if plasma is 55% of blood and water's 92% of the plasma of that 55%, then it's probably safe to say that roughly 50% of your blood is going to be water, right? 55% is plasma. The bulk of plasma is water. So roughly 50 to 55% of your blood is just water. Gosh, I know. I should have warned you. I should have given you a caveat at the beginning of the class today that there were going to be numbers. Well, anyway. So you guys are getting into nursing. So you're already getting into science. So math is a big deal in nursing. So if you don't like math, you better learn to like it, because nursing is a lot of numbers and math, and I don't know. Hopefully they tell you that. If you just be neutral about math, you don't hate it though. Don't dislike it. Just accept it. All right, it's everywhere. So anyway, what's the rest of plasma? Most of it's water. Well, you've got what are called plasma proteins. So we'll look at a couple of those in just a second. And then we've got a few kind of hormones and enzymes, of course, floating around in plasma. And then naturally we see nutrients and wastes. We might see some gases as well. All right, so let's go all the way across. We start with water. 92% of plasma is water. What is it? It's a fluid, of course. Where do we get it? Right, we have to drink it. Right, we consume water. How does it get into the bloodstream? It's absorbed by the intestinal tract, and absorbed by the intestinal tract. Okay, so you drink water, intestines absorb it, put it into the bloodstream. We also see water as a byproduct of metabolism. So next semester, when we study metabolism in more detail, we'll see oftentimes when we have a chemical reaction, one of the products from a chemical reaction is going to be water. So we'll pay attention to that as well. So that's good. We do recycle water, right? So a lot of our patients, man, and hopefully not a lot of you, but a lot of our patients, they don't like water. They don't drink enough water. They may drink soda or pop. We're in Wisconsin. I don't know. It's both, right? We're on the Illinois border here. So soda pop. We'll cover both of them. So yeah, a lot of patients drink soda pop. They drink coffee. They drink tea. They drink a lot of alcohol or beer. So there's water in those things, of course, but it's not good water necessarily. So we do want to make sure that our patients are cognizant of the importance of actual water. So anyway, bottled water. When I was a kid, we just drank. I'm old, so they didn't really sell bottled water. That wasn't really marketed back in the 70s and the early 80s. Gosh, man, if I would have known water would be bottled water be a commodity like it is, I would have, I would have done nothing but consume it and drink it. So that's what ended up happening. But anyway, right? So we just drank it out of the faucet, turned it on, and Winter was awesome for drinking water out of the faucet. It was nice and cold, ice cold water. It was out of a well, though. Ooh, yeah, I was a farm kid, so there's well. We drank out from well water. You know, if you ever wonder what's wrong with me, it's probably that well water as a kid. But anyway, what do we need water for? It's a transport medium. All right. In other words, it's what all of this other stuff is getting transported within. It's water soluble. All right, let's look at these plasma proteins. We do have three plasma proteins. Albumin is the first one. It's the most numerous of the plasma proteins. Okay. Albumin is what kind of gives plasma that whitish, creamish look to it. If you've ever seen blood centrifuged and you've seen plasma get separated, it does have kind of a milky, creamy appearance. It's not completely clear because it's not 100% water, right? It's 92%. So alba means white. So albumin is just like a whitish colored globular protein. It's produced in the liver, and its role is basically to maintain osmotic balance. So that the constant, this gets into some physiology, so I want to be careful how deep we go, but for now, just osmotic concentration has to do with the ability of water to move to dilute somewhere. We did a little bit with osmosis, so you guys recall we did cell transport mechanisms, right? You did hyperosmotic, hypoosmotic, and isotonic. So, or hypertonic, hypotonic, and isotonic. So albumin, being that it's a plasma protein, it helps to maintain what we call osmolarity or osmotic concentration. It's a so like a solid inside of the solute, which is the water. So amount of albumin can oftentimes determine how much water we retain from the kidneys or how much water we get rid of. So albumin helps with maintenance of water balance. So the kidneys play a major role in albumin balance and thusly water balance. So anyway, that gets into too much physiology for now, or maybe it was just enough for you. Transport lipid molecules. So albumin does help with transportation of some lipid molecules. The other two are globulins and fibrinogen. We do have different types of globulins, alpha, beta, and gamma globulins. One of this third one, immunoglobulins, is maybe something you've heard of. You've heard of antibodies. So immunoglobulins are a lot like antibodies, or even more specifically, they are a type of antibody, immunoglobulins. So they play a role in immune responses. They are abbreviated clinically as IG, okay, immunoglobulin, IG. So next week, when we get into the immune system, and then a little bit next semester, we'll look at different types of immunoglobulins. IgE, for example. So immunoglobulins, capital I, little g, immunoglobulin, and then they're lettered. So IgA, IgB, IgC, etc. So these are types of antibodies. Okay, so they have, some are related to allergy and allergic reactions. So anyway, we'll look at immunoglobulins more next week or the weekend, whenever we get to immune system. Then we've just got more transport mechanisms and osmotic balancers with these other two. And then the last plasma protein is called fibrinogen. This is extremely important, again, coming from the liver. This is for blood clotting. It's a blood clotting mechanism in hemostasis. This is different than homeostasis, right? Homeostasis is balance. Hemostasis means we're going to get blood. We see heme in there, first of all. So we know blood is involved, iron is involved, red blood cells are involved. So hemostasis, we need to kind of slow or stop or sustain the flow of blood. So hemostasis usually involves preventing blood from leaving an area. So we need blood clotting. This happens when there's a breach or a break in a blood vessel. So if there's an injury to a blood vessel, whether it's external, some sort of a cut or something, or whether it's internal bleeding from an aneurysm that ruptured, or maybe we have just some capillary walls that have gotten weak. Either way, if blood is leaving its blood vessel tubing, then we need to put a patch on the lining of the blood vessel and stop the bleeding. That's hemostasis. And blood clotting and creating kind of a net is what fibrinogen does. So fibrinogen will generate something, fibrinogen. Switch it around, it says fibrin, generates fibrin. So fibrinogen generates fibrin. Fibrin is kind of like a fibrous net that we'll see coming up shortly when we'll talk more about hemostasis in a few minutes and blood clotting. But anyway, that's good, right? We need that. We need to be able to stop blood. We may have some patients that have issues with blood clotting. So is it due to a plasma protein that's lacking, or is it due to platelet issues? So we haven't done platelets really much yet, so we'll see that in just a few minutes. All right, so lastly, we've got some hormones and enzymes, of course, in our plasma, and those come from a variety of places, primarily for regulating different body functions. And then, of course, the nutrients and the gases and the waste products. Yeah, that's all either absorbed from our intestines if it's nutrients, or it's cellular waste from as byproducts from cellular metabolism. So anyway, respiratory waste, gas waste as well, carbon dioxide, something called carbonic acid, carbonic anhydrase. So we'll see some respiratory waste or gas waste as well. So anyhow, that's plasma. There's a lot going on in plasma. Again, roughly 55% of the total blood volume is plasma. And what is plasma? Well, it's primarily water, and it's got a whole bunch of other little bits that make up the rest. Okay. 92% water, 8% everything else. And again, what is that everything else? Plasma proteins primarily, with a little bit of hormone, a little bit of enzyme, and a little bit of nutrients and a little bit of waste. Okay, so there's a lot going on in plasma. And again, we can do part of the blood draw process, or CBC. We could analyze a percentage of albumin. Maybe they have a low albumin percentage that's creating some osmotic balance problems with the kidneys and fluid balance with the kidneys. So the person is extremely dehydrated because, again, albumin is going to be drawing water typically towards it. So it helps with, again, keeping us hydrated. If we have really low albumin levels, that could lead to losing water, because water usually follows albumin. It usually follows sodium. It usually follows chloride ions. So that's what water is doing. Okay. So when we want to retain water, we need to retain sodium, and albumin percentages have to be correct. We could have some, again, some immune issues. We have some immunoglobulin levels that are low. These, again, are coming from plasma, specialized cells in the plasma. So, and there's so many environmental exposure to stuff that alters plasma levels. It alters plasma quality. A lot of people donate plasma for money, right? So especially in bigger cities, they have plasma donation centers where you can get on kind of like a plasma plan and come in weekly or every couple of weeks or once a month or whatever, and they give you $20, $40, $80, just depends on what your schedule is. So I wouldn't recommend it, but it is something that some folks do. And what are they doing when they're getting plasma? Well, they're getting everything, right? They're getting your blood. They're not just getting the plasma. But anyway, this is what they're getting. Any number or amounts of this type of stuff. We're going to see immunoglobulin stem cells contained within plasma. Okay, so who knows what they're doing with it? Let's see, major blood components, formed elements. Okay, so everything else, right? So it's plasma, roughly 55%, everything else, roughly 45%. So out of the everything else group, remember, almost all of it is going to be red blood cells. So we do start to see some sciencey terminology, erythrocytes. That erythro means red. So erythrocyte, cyte means cell. So these are red cells, also known as RBCs or red blood cells. Okay. And again, where do we find red blood cells? We find them produced in red bone marrow. And what is the function of red blood cells? Again, transportation primarily of oxygen. Okay, some CO2 is delivered. This semester, and by the way, chapter 18 on blood, most of that chapter is relevant for us now. There might be a couple of items in there. It's not a real long chapter. So if you go through and skim through chapter 18 in OpenStax, most of what's in there is pretty straightforward regarding anatomy. There's very little physiology stuff. Now, when we go into chapter 19 on Thursday, we're going to see that we're probably only going to do the first section of chapter 19. The bulk, which is on the heart, the bulk of chapter 19 is going to be physiology stuff, transportation mechanisms. Okay, so for now, when it comes to the physiology of blood, we're really just thinking about red blood cells produced in bone marrow, and they primarily are going to transport oxygen. Okay, oxygen transport. That's again why hematocrit and hemoglobin levels are so important. All right, and then we've got leukocytes and platelets. Okay. This is a misprint right here. This platelets / one that should be down here, which it is. Okay, so we're doing leuco. Leuco also means white. We saw alba means white. Leuco means white. I think alba is Latin and leuco is Greek. But leukocytes, this site means cell. So these are white blood cells. Now, white blood cells have 5 different types. Okay, there are 5 categories of white blood cells. And they break them down into being either granular or agranular. Okay, granular, agranular. The only difference is we put an A in front. And again, those of you who've had med term, or maybe you've seen it this semester and you've got it down. A in front of something means without or not, right? So A means without. So agranular means without granules. Okay, granular means with granules. Now, what does that mean? That just means when we look under the microscope at a blood smear, we would see white blood cells with little granules in their cytoplasm that got stained. And then we'd see some white blood cells that wouldn't have granules in their cytoplasm. So we'll see that in more detail coming up a bit later. But there are 3 granular leukocytes. These are the fills. Okay, granulars are the fill. Okay, so there are 3 fills. Fill means affinity for or a lover of. Okay, affinity or love of. So this has to do with pH levels generally, and it has to do with the staining techniques that we use to stain blood or to do a blood smear. So anyway, that's where they came up with these terms: neutrophil, eosinophil, and basophil. So, some of you have maybe had or worked with like pH strips at some point, the little pieces of paper that turn color. They're either kind of a bluish color, and you dip it into a liquid, and if the liquid is acidic, the blue paper will turn pink, right? We have pink paper. We could put that into something that's basic or neutral, or more basic, and it'll turn the color more of a blue. So blue color generally implies that we're dealing with a basic pH. Pink color means we're dealing with an acidic pH. So same holds true with staining of cells. So when we're looking at a blood smear, we're going to see, which we'll do on Wednesday or on Thursday. We'll look at some blood smears, but we're going to see that um, the white blood cells are usually very few in number, for one thing. Secondly, we're going to see that they're usually a little bit bigger than red blood cells. Okay. The other thing about white blood cells and staining is, when we do microscope staining, the stain goes after typically the nucleus of the DNA and the chromatin of the nucleus. So red blood cells do not have a nucleus. You'll remember from several weeks ago. So when we stain blood, red blood cells they don't take on the stain, but they do have iron or in them. So they do show up as kind of a reddish, dark reddish, pinkish color, and they're very tiny. So red blood cells show up in very numerous quantities in a blood smear. The white blood cells are going to show up as being slightly different. They're going to be a little bit larger. They're going to stain maybe a purple kind of a color. That might be maybe a leukocyte, whereas or a neutrophil, because it's neutral. So it may stain kind of a purplish color. Eosinophils are acidic lovers. They love eosin, which means acid, pH level. So they're going to be more of a pink color. Basophils are going to be more of a deeper blue color, like a darker blue, blue violet even. So they like basicity. So when we look at when we look at a blood smear, white blood cells, typically you won't see very many, for one. And then if you do see any, you're probably going to be seeing a neutrophil out of this group. If you see any with granules in them, it's likely going to be a neutrophil. Okay. These deal with basic immunity. So they do what we call non-specific immunity. Non-specific immunity has to do with kind of vacuuming up waste. If there's some sort of a bacteria, if there's something, it could be anything that doesn't look like it belongs in the bloodstream, granular leukocytes will kind of keep things cleaned up. Now, eosinophils go after like parasites. So if we do have like an intestinal parasite going on, so a patient comes in, everything's normal with them, but they've come in because they can't keep on any weight. They've been losing weight like crazy, even though they've been eating like normal. That and nothing's changed in the person's life other than extreme weight loss. Well, that definitely sounds alarms in our ears. So we may run a CBC first off, just to make sure that everything's on the up and up, and we can do what's called a differential white blood cell count. So we can break down how many of each of these different white blood cell types are there. So if we see a high percent, there should only be a couple, 2% maybe of eosinophils. If we see like 10% of the white blood cell count is eosinophils, that could be an indicator that I have some sort of intestinal parasite that's consuming the food that you're consuming. That's why you're losing weight. So that, hopefully, if that is why the person's come in, hopefully that is the answer, because we can treat that in 2 seconds, and it's gone. And then they're they'll be back to normal. Other reasons why you'd have excessive and extreme weight loss out of nowhere are not that easy, are usually not good. Um, so anyway, we want to stay with good news, and so that maybe it could just be a thyroid issue. They might have an metabolic, hyperthyroid that's burning their energy too fast. So that it could be, they might have a thyroid issue too. So anyway, stomach parasite or intestinal parasite is easy to get rid of for the most part. A thyroid problem could be long term and a lot of medication and treatment. It could also be some sort of cancer in the body, and that's why they're losing so much weight. So, usually, an extreme weight loss without any provocation is a bad is bad. But I guess anytime people come to the clinic, it's bad. It seems like. But anyway, God, gloom and doom. I'm even sinking further. Pretty soon you won't see anything but my forehead. All right, I'll get on to some lighter sides of stuff. So anyway, granular leukocytes. These are white blood cells that have granules in them, and they're the fills. All right, agranular leukocytes, lymphocytes, and monocytes. So these do not have granules. They do have a nucleus. They are white blood cells. All white blood cells do have a nucleus. That's why they stain so well. Lymphocytes are going to be produced in bone marrow as well. We would also find some lymphocytes produced maybe in the spleen or some other lymphatic tissue in the body, maybe some lymph nodes or lymph glands. The thymus gland, back up. The thymus gland does a lot of work, not necessarily producing a lot in the way of lymphocytes. We ever have what are called B cell lymphocytes. So this is a teaser trailer for next week or the week after when we get into immunity. But T cell lymphocytes, B cell lymphocytes, you've maybe heard those terms before. B cell lymphocytes are born and raised and stay and originate and never, they travel throughout the body, but those are B cell, bone marrow lymphocytes. T cell lymphocytes are thymus lymphocytes. So it says other lymphatic tissue that's probably thinking, we are thinking thymus gland. So T cell lymphocytes, T means thymus gland. Okay, T cell lymphocytes. And again, these are going to do more with specific immunity. Okay, specific immunity. So they're going to go after specific virus. They have specific chemistry and codes that they're able to lock onto with these antibodies and antigen combinations to again go after specifics. Monocytes, red bone marrow. These are more non-specific immune functions. We'll look at monocytes. We'll look at all of these when we get to the immune chapter. So this is just your introduction to leukocytes. Okay. Granular, agranular, always relate white blood cells or leukocytes to the immune system. All right, lastly, we have what are called platelets. Again, less than 1% of your blood volume are platelets. These, I don't have it written in here, but we could also call platelets, could be called thrombocytes. Oops. I don't know what just happened. There we go. Oh, I pushed the notes, but thrombocytes. Okay. Thrombo, THROMBO, thrombocytes. Okay. If red blood cells are going to get a fancy name, erythrocytes, white blood cells get the word leukocyte. Platelets need a science name, so we call them thrombocytes. These come from red bone marrow, specifically what are called megakaryocytes. So we'll look, this isn't super important, but notice red bone marrow, bone marrow, red bone. So we know this already, right? That blood cells are produced in the bone marrow. All right. So what do platelets do? They help with hemostasis. Again, that relates to blood clotting, mechanisms. Now, this slide is not super important for you to grasp right now. We get into this a little bit more next semester when we talk about hematopoiesis. Sounds like a mouthful, but hemato, again, meaning something to do with blood. Hematopoiesis. Poiesis has to do with the production of. So hematopoietic system of bone marrow. So this just shows us we've got different types of stem cells. We see what are called pluripotent stem cells. So we see what are called myeloid stem cells and lymphoid stem cells that come off of these what are called, again, pluripotent stem cells. Stem cell, there are different types of stem cells. You guys have probably all heard the words stem cell at some point. And so stem cells are in essence like baby cells, or they're soon to be cells, like actual functional cells. They're like pre-cells, I suppose. So we have stem cells that are located certainly when a gamete, a sperm, meets another gamete, an egg, and we have fertilization. Right away, we're going to have the differentiation of cells into tissues and organs into all of these different layers. And so those are all a certain specific type of stem cells. And then once we're born and our bodies are going through this constant process of producing different cells, right? Very few cells live the lifespan that we live, right? Like maybe neurons, right? Muscle cells, cardiac muscle cells. You're born with what you have, you die with what you have. But most cells are not that way. So red blood cells especially live about 120 days. It's not very long. So we're constantly producing red blood cells. So we have pluripotent stem cells that are maybe more specific to, so you have embryonic stem cells, right, dealing with the embryo, and then pluripotent stem cells that are more specific to us as living, breathing, womb, outside of the womb, cord's been cut. So now we have our own system of producing new cells. So anyway, myeloid stem cells from bone marrow are going to be producing all of the blood cells, really, except for the lymphocytes. Lymphocyte, remember, is one type of leukocyte, a granular leukocyte, a granular leukocyte, not a granular leukocyte called a lymphocyte. It's a mouthful, right? That's why we save immunity till you give you a little bit now and give you more later. But yeah, the only cell of all of these cells we just looked at, red blood cells, 5 different types of white blood cells, and platelets. So 7 cells, okay, only one comes from a lymphoid stem cell. The other ones come from myeloid stem cell. So if you're ever asked, what type of stem cell does a monocyte come from? What type of stem cell does an eosinophil come from? What type of stem cell does a red blood cell or erythrocyte come from, or a platelet come from? The answer is going to be myeloid stem cell. The only one that isn't out of all these blood cells is the one that has the word lymph in it. Okay. Lymphoid. Okay. Lymphocytes. All right. So anyway. So, and then it shows we've got the T lymphocyte and the B lymphocyte. And they've got another one over here called the natural killer cell. It comes from the thymus gland as well. So anyway, not to get too technical about stem cell stuff, but yeah, stem cells, myeloid stem cells. Those are going to be your bulk of your blood cells. Now let's look at a few numbers. Again, I don't want to spend too much time on this, but these are some pretty good descriptive terms as well of what we went through. And then we'll move on to a couple other things, and that's it. That's all I have for today. So erythrocytes, again, those are red blood cells. No major subtype. It's a red blood cell. Okay. Numbers present per microliter, not milliliter, per microliter. Okay. 5.2 million per microliter. Now, how much space does a microliter probably take up? Probably like the tip of your pinky. The amount of blood that would fit into the tip of your pinky. I keep seeing my thumb. Yeah, just the tip of your pinky. That's about a microliter. Not much. Small amount. 5.2 million red blood cells. And again, they're flattened, kind of a little bit concave, kind of like a gummy saver that hasn't had sometimes you get a gummy saver, right? If you ever get gummy savers, the hole hasn't been punched out all the way. So it's got the little depression, but there's still a little bit of gummy in the center. Those extra gummy, yummy. All right. So anyway, that's kind of what they look like a little bit. No nucleus, okay, and they're pale in color. And again, the function is transportation of oxygen. That's primary. It does transport a little CO2. And again, their lifespan is only about 120 days. Okay. Now, when we look at leukocytes, we see the total amount of white blood cells is about 7,000 per microliter. Okay. So when we do a CBC, they may come back and say the white blood count is 15,000 or 12,000. Okay, that means we've probably got an infection of some sort. Okay, so 5 to 10,000, that's your normal range for white blood cell count. Okay. And again, they're nucleated, so they're going to have that obvious dark staining nucleus. So I have 3 of them pulled up here, your 3 granulocytes. You could sort of see some granules inside of the cytoplasm of those. Okay, but they're going to be dark staining. And again, body defense mechanisms, immunity. And again, their lifespan is usually pretty short. Few minutes, hours, up to a few days. Because white blood cells are kind of as needed. If there's a specific infection, you're going to get the release. If we've got inflammatory issues, okay. So let's take a peek. So granulocytes. Okay, so out of the 7,000, the granulocytes make up more than half. So about 4,400 out of 7,000. Okay. Again, these are non-specific. This has to do with what we call innate immunity. Innate immunity versus acquired immunity. So innate immunity is what you're born with. This is your most basic resistance to disease. Okay, that's going to come from these guys. They generally, again, they're in your bloodstream in less than 1% numbers. Those numbers can go up if there's an infection. All right, so the most numerous of the granulocytes and the most numerous of all of your white blood cells are the neutrophils. Okay, and again, kind of a lightish, kind of lilac-ish, real light purple color, neutrophil. Because remember, the 2 spectra for acidity is pH is acid and base. Acid is pink, base is blue. Pink and blue together, well, red and blue, so they kind of make kind of a pinkish purplish color. Okay, so that's what you get with a neutrophil. they're what we call phagocytic. So they like to engulf gunk and debris that's floating around in the plasma and consume it. So these guys eat bacteria that are floating around. They can release specialized chemicals. So these granules have chemicals in them, so they could release some of these granules, and these granules will then kind of open up and release like a toxic spray that'll kill some sort of microbe or microorganism. And again, minutes to days is all they live. And then we've got, again, the eosinophils and the basophils. Eosinophil are going to be more pink. They're more acidic lovers. Basophils are going to be more blue, deeper blue, purple, dark violet color. Again, they're leaning towards being basic, lovers of basicity. So anyway, these eosinophils, antibody release antihistamines. So these might be some anti-inflammatory responses. Again, parasitic infections, folks with extreme allergies may have higher numbers of eosinophils. Basophils promote inflammation. They're the least common leukocyte. You don't have very many basophils generally. We go into the agranulocytes and we look at lymphocytes and monocytes. And again, we do see some granules. They're just not that abundant. Typically, you're not going to see much of any. Lymphocytes have an extremely large nucleus, so they show up in a way that it's usually not lobed. You can kind of see how the nucleus of these is more lobed, whereas you've got more of a big kind of a blobby circle for the nucleus of a lymphocyte. These are the second most numerous of all of your white blood cells. So again, neutrophils are the most numerous, and then lymphocytes. Everybody else is in pretty low numbers for the most part. And these lymphocytes, remember, are specific immunity. So these deal with B cell, T cell, thymus gland, and bone marrow. These deal with direct linkage and attacks on specific pathogens. We'll see what are called natural killer cells coming up when we do immunity. Okay, so anyway, we'll see lymphocytes extensively in about 2 weeks. I mean, it's called the lymphatic system, so we're probably going to see lymphocytes play a major role again in keeping our immune system healthy and keeping pathogenic invaders at bay. Lots of types and again, lifespan potentially of many years for these certain lymphocytes. All right, so anyway, monocytes are the last white blood cells. Okay. These again are agranular. They do have kind of a horseshoe-shaped nucleus. These are the largest of all the white blood cells, so they'll stick out quite a bit. They're a white or red blood cells only maybe about 6 to 8 microns in diameter, micrometers in diameter, very tiny. So 1,000th of a millimeter. And monocytes, these might be like close to 20 microns. So these might be like 4 times the size of a red blood cell, 3 to 4 times. Okay. These are also phagocytic. These work on a lot of kind of cleaning up useless cells that remain, cells that have died and aren't really doing much. Monocytes can kind of help engulf and clean up some of that. They also engulf pathogens and foreign invaders. Let's see. Lastly are what we call the thrombocytes or platelets. These are the tiniest of all of our cellular aspects. And again, in one little tip of the finger, you're going to have about 350,000 platelets, even though that makes up less than 1% of the total blood volume, because again, they're tiny fragments. They're very tiny. They look like little specks in a blood smear. And they, again, deal with blood stopping, platelet plugs, hemostasis, blood clotting. Okay, red blood cells, again, are going to be kind of concave circles, and we're going to see, again, facilitating gas exchange. The main component of a red, no nucleus in a red blood cell, the main component of a red blood cell is this. It's called hemoglobin. And hemoglobin is going to be 4 quadrants. You can see 4 different chains. We have what's called a beta chain 1, beta chain 2, alpha chain 1, alpha chain 2. That's going way beyond what you need to worry about at the moment. You just need to know hemoglobin has 4 globins. Globular just means globular proteins. For hemoglobin. Globin means globular protein. Hemo, remember, means iron. So we do see 1, 2, 3, 4 irons, iron ions attached. That's a tough one to say. Okay, well, let's just call them irons. We see 4 irons in 1 hemoglobin. Okay. Why is that important? Oxygen is what attaches to these hemes. Okay, they call this a heme group. Okay, the iron attached to the globin is called a heme. Okay, so that oxygen attaches to the iron and then that heme. All right. So one, if your ass is a lot of numbers today, I'm sorry, but you got to do what you got to do. There are 4 oxygens can attach to 1 hemoglobin. Now, 1 red blood cell has several hundred million hemoglobins. Okay. 1 red blood cell, we'll say 250. We'll make this easy math, if there is such a thing. 1 red blood cell can have, so we'll say 250 million hemoglobins. Each hemoglobin can have 4 oxygens attached to it. So 250 million hemoglobins in 1 red blood cell. 4 oxygens attached to each hemoglobin. 250 million times 4 is 1 billion. So each red blood cell can carry roughly 1 billion oxygens. And remember, the tip of your finger has 5 to 4 to 5 million red blood cells in the tip of your finger. And each one of those red blood cells is carrying 1 billion oxygen molecules. You think oxygen is pretty tiny? Yeah. Oh, yeah. You can't even see a red blood cell without a microscope. 1 red blood cell can carry 1 billion oxygens. That's a lot of big numbers, especially on a Tuesday. These next few slides, real quick, real brief. We've got some leukocyte activity. Okay, so remember, leukocytes are white blood cells. So what we're seeing is we've got some sort of a capillary, and the capillary is going to have little pores. They call them fenestras or windows. We'll see that. Well, they call them fenestrae, but a fenestra is a window. Okay. Eosinophil, monocyte, neutrophil. Okay. Just for example, what they're showing. Now, what's this out here? This would be maybe the surface of your pinky. Maybe you got a paper cut. Okay, so you got a little paper cut right here. So this is the outside world over here. Little paper cut occurs. There could be some stuff outside. There could be stuff in the paper, right? Some micro particles on that piece of paper. Either way, we now have a breach. All right. And that breach. So this line here is showing that we've got some nervous system signaling. We've got the blood. This is probably epidermis, dermis. Okay. So remember, the dermis has all the blood supply. So we breach through the epidermis and we make it through that basement membrane into the dermis. At that point, we're going to see some alarm bells going off. Okay. Pathogens are already lining up. Pathogens are the bad guys. So white blood cells, notice they're going to start squeezing through these little windows or fenestrae. Okay. And they're going to head over to the site of infection. Now, what are they going to do in this area? Well, multiple things. A lot of these white blood cells have chemicals. So the granular sites, they can release some granules that release some toxic chemicals that kill those bacteria or those pathogens. Okay. Others, so we can see this eosinophil releasing cytotoxic chemicals. Okay, so this is releasing granules with cytotoxic chemicals. Then we have the macrophage. This again, this is probably going to be a monocyte. Notice there's no granules. It's very large, so the monocyte's going to come in and kind of engulf and eat, maybe eat the pathogen. Yeah. So phagocytosis just means means eating. Process of a cell eating. Macrophage means big eater. Okay, and monocytes are big eaters. They could come in and pig out. Okay. So when there's a breach, we've got white blood cells show up, take care of business. Okay, so we see the neutrophil, eosinophil, basophil representations. Again, we've got all of these are granular. So we see different grains. Okay. Multi-lobes of the neutrophil nucleus. We have a double lobed with the eosinophil. And then we get kind of a double lobe over here, but again, more of a deeper purple versus a brighter pink. So this is a cytophil. This is a basophil. Neutrophil is right down the middle, so it gets kind of that light purplish color. And again, where are all of these coming from? Coming from bone marrow primarily. When we look at the agranulocytes, so no granules, we primarily are thinking of the lymphocytes. Okay, lymphocytes. And then, and again, they're more specific to the immunity. We're going to see those in more detail either next week or the week after. And then monocytes are the other agranulocyte. So, and they're the largest. They do a lot of just kind of engulfing and eating big particles. So that takes us to the platelets. And again, platelets are going to come from what we called megakaryocytes. These can, we go back to this slide. So platelets are all the way down here. Again, they're coming from that myeloid stem cell from bone marrow. And then we're going to see different types of myeloid stem cells. The megakaryocyte is going to be what kind of where platelets kind of break off of. Karyo means corn. So let me go back to that megakaryo. This just basically means big nucleus cell, megakaryocyte. And it's going to have these, so you can see it's got a huge nucleus. So you got the myeloid stem cell, megakaryoblast to a megakaryocyte. These little extensions are what platelets come off of. Okay, so this again hanging out in the bone marrow, and these little extensions kind of pump out platelets, and platelets again are what we call thrombocytes. And what kind of triggers platelets to be active is typically going to be some sort of hormone or chemical that's been released because there's a need for clotting. We have a breach somewhere in the bloodstream, so we need some sort of a clotting mechanism. Okay, so and again, I have a couple of slides coming up in a few minutes about clotting. So we'll see platelets again. But next semester, again, in advance, we do more with clotting. So anyway, just throwing in these are actual blood smears. So you can see red blood cells, these nice pink. There's no nucleus, so we don't get the staining occurring inside of the blood cells, the red blood cells. And then notice all of these other items are a little bit larger for one than the red blood cells, but they also stain. So we know these are going to be white blood cells. Now, again, what type of white blood cell is it? Well, first of all, we see this has a lot of little grains or specks. This has a lot of little specks or grains, and it's bright pink. And that's an indicator of an eosinophil. And then we have more granules here, but look at this multi-lobed jobber. It's a neutrophil. These are the most numerous. There are not a lot bigger than a red blood cell, maybe just slightly, but usually you'll see some neutrophils when you're looking at a blood smear. But you might also see one or the other of these guys. Lymphocytes are second most numerous. So you're likely on a normal blood smear, you might see a couple of these guys, a neutrophil or a lymphocyte. Okay. And again, with the monocyte and lymphocyte, there are no granules in the cytoplasm. We see a lymphocyte as that enormous nucleus typically. It's a little bit more unusual compared to the other ones. And again, we see that maturing in lymphoid tissue. Now, let's take a quick look at hemostasis or blood clotting. Again, we've got a breach somewhere in a blood vessel. This could be a capillary. So we're going to see white blood cells kind of leave the area, right? They want to engulf any pathogens that might be around. But platelets are going to come in because they're going to want to stop the bleeding. So one of the first things that first of all, these are these blood vessels. We haven't done anything with blood vessels yet. So next week we'll get into those. But these blood vessels are smooth muscle lining, or well, not lining, they're smooth muscle with an epithelial lining. Okay, so within these tubes or these vessels is going to be smooth muscle. That smooth muscle is innervated. So as soon as there's some sort of a breach here in a blood vessel, it's going to trigger the nervous system stimuli to travel up to the brain. It may not even, it's going to get to the brain, but before it ever does, we can get a pretty quick reflex, a motor response to come out. So that's what number 2 is going to show. So the stimulus is number 1. We've got a breach in the blood vessel. So the stimulus is going to come in. The response out is going to be some sort of what we call vasoconstriction. So we're going to get some vascular spasm or vessels spasming. Vascular means vessel. So you're going to get that smooth muscle spasming. So we shrink up. This makes sense, right? We don't want a bunch of blood to continue flowing out and leaving the compartment. So we're going to shrink naturally the blood vessels, vasoconstriction. Then we go kind of blow up. So the next slide, it just takes and focuses really on this section here. All right, so now we're just looking at kind of the one part of that break. And what we need to do now is form what they call a platelet plug. So we're going to put kind of a plug right here and right here. So that's what we're showing next is a platelet plug. And how am I going to get all, so I already have platelets, right? First of all, platelets are kind of sticky. Platelets are a little bit star shaped, and we kind of saw that back here. You can't really see them down here, but the megakaryocyte star shape. But as these break off, they have kind of platelets have kind of jagged edges to them. And you kind of see one right here. See a platelet kind of converts. It's got that jagged edge. It gets some stickum going to it. And so as these little platelets start flowing through, they're going to get stuck in what we call a net. And the net is like is kind of fibrous. You could see uh, uh, we start to get some collagen fibers built up. So anyway, this platelet plug is basically a bunch of collagen fibers that have broken off from the lining. Okay, so where we have we have blood a blood vessel, we've broken it. Now we've got some tendrils or some fibers where we tore the blood vessel. So you can see them up here better. Okay, so there's going to be some collagen fibers. Well, these collagen fibers are going to kind of adhere with one another and allow for these platelets to stick. And so that's called a platelet plug. All right. Well, it's not great, but it's pretty darn good. It's going to stop. So you can still see there's some red blood cells still kind of leaking out of here. So, but anyhow, more and more platelets, bigger and bigger plug. The other thing we're going to start to do is form a blood clot. So we need this as this platelet plug forms. These red blood cells are going to get kind of caught in this little web as well. We've started converting fibrinogen, and remember, fibrinogen is going to be coming from one of your plasma proteins. So we've got a plasma protein, fibrinogen. It's going to convert to fibrin, and fibrin is just basically means fibrous net. So a bunch of fibers. Okay, so these fibrin strands are going to continue to collect platelets. They continue now they're able to collect red blood cells too. So here, red blood cells are kind of seeping out. Over here, we've now got a more of a net, more of a fibrous thing going on here. At this point, we have what's called a blood clot. Okay. And this science word is called a thrombus. So this is a thrombus. So there are a couple other chemicals that we see called prothrombin leading to thrombin. So that's also going to be a couple of the chemical triggers to get this to happen. Now, there's a link here that you can click. It'll take you into OpenStax. So I'm going to do that now. And what it's going to show us is, move this over here. It's going to show these pathways. So let me blow this up. So we've got, and this is all FYI. That's why I decided I put the link in there. I wasn't going to copy and paste and create a slide with this stuff. I really just want to show you just the complexity of what are called clotting factors. So we see all of these different clotting factors, which are chemicals that are going to lead to the final pathway to get that fibrin clot. So a lot is happening from the point of injuring that vessel wall to getting a little tiny clot form to stop that bleeding. Prothrombin leads to thrombin, and fibrinogen leads to fibrin. And so thrombin and fibrin combine at the active site to create this plug, or this bigger than a plug now. It's an actual blood clot. And down here, again, let me go back up. These are all these Roman numerals. These are not cranial nerves because we've seen Roman numerals before. So I don't want you to get confused. These Roman numerals are the clotting factors. So fibrinogen 1, fibrin 1, fibrin 1A, prothrombin 2, thrombin 2A, and so on down. Here's clotting factor 3. There we go. So here they are. Here are all the clotting factors. You've got 13 of them. Do you guys need to know these clotting factors? No, definitely not. However, I think knowing fibrinogen and fibrin, prothrombin and thrombin, I think if you heard those two terms, this little batch right here, I would say next semester we do that. I guess what I'm saying is this is just an introduction to some of the physiology of what's going on with platelets, okay, and with blood, with hemostasis, blood coagulation, and blood clotting. For now, knowing red blood cells, white blood cells, and platelets, that's good. Know a little bit of the details about each one. Now, when it comes to thrombin and fibrin, I think for now, know that those are those are clotting factors that are part of creating a blood clot. And the names tell us a lot. Remember, thrombus is a clot. So thrombin means a chemical that leads to a blood clot. So remember, most of what you do is multiple choice anyway. When you're seeing things written out, you can make some pretty good deductions. When we have pro in front of something, it means precedes it. So prothrombin is the precursor to thrombin. Okay. Another way of seeing a precursor in medical jargon is a GEN at the end. Gen means generates. So fibrinogen generates fibrin. Okay, so you guys see that, the way the arrows roll? Prothrombin precedes thrombin. So prothrombin leads to thrombin. Fibrinogen leads to fibrin. Okay, these are the clotting factors. Just two of them, prothrombin and fibrinogen. Those are the only two out of, I guess what my point is, the only two you need to know, I would say, are those out of those 13. We'll talk again next semester about calcium ions and clotting and some of these other things that are going on. All right, so back to our slides. All right. You guys back over there. There we go. All right, we're on a roll. The last, I think it's just the last thing we're doing is blood typing. So the last thing I want to do today is blood typing. And then guys, go enjoy the rest of I don't know, it might be kind of rainy, but temperature wise, we're not going to see these temps until probably March. So you may want to relish in 60s one last day. So blood typing. I don't know if you guys know your blood types. Now, next semester, in advanced A&P, I do blood type. We do a little bit of blood typing. We introduce you to blood typing in general, and then some of us do a little kind of a lab in general. Some of us do the lab in advanced. I wait and do it in advanced, um, just kind of as a memory refresher. So if you do sign up for a face-to-face or a hybrid class, you may do blood typing. If not, your clinical, whenever you have any type of clinical laboratory type of class, you will do blood typing. My point is, if you don't know your blood typing, if you don't really understand or grasp what's going on with it now, it's okay. You will have plenty of opportunity to understand blood typing and even know what your blood type is, because I'm pretty sure that in one of your lab courses that you'll take, you guys will poke each other's fingers and do the antigens and see what your blood types are. So anyhow, so I just want to introduce you to it. I don't want you to get too stressed out about trying to get it or not get it. There's just a few tidbits that I want you to take away from this. First off, this is FYI. This first slide just kind of introduces you to blood typing. I think all of you know that there's A blood type, B blood type, AB blood type, and O blood type. Okay, so we call it the ABO typing system. Okay, so we can see along the left, we've got A, B, B, A, B, and O, O. And we have two of each because there's another factor involved with blood typing, and it's called the rhesus factor. And you can see the spelling, Rhesus, the rhesus factor. That's blood typing, first of all, deals with the presence of what are called antigens on the surface of red blood cells. Okay, antigens are going to be surface markers on cells, not just red blood cells, but all cells. And we've maybe mentioned this in the past briefly when we were studying cell membranes and cell transport and communication mechanisms. And so antigens are little markers on the surface of cells, and they help with communication. They're going to be shaped in certain ways that allow them to link with and communicate with other cells. And the way they can communicate with other cells by the presence of these antigens is through an intermediary chemical called an antibody. Okay, antibodies. So antibodies are little chemicals, molecules that are swimming around in your blood that have specialized structures or shapes that enable them to attach or not attach to antigens on the surface of certain cells. So we have what are called, the plasma antigens from red blood cells. Now, red blood cells and the antigen that is on their surface are how they're named. So there are actually three, there are more, there's a ton, but for blood typing, there are three antigen possibilities that could be on the surface of a red blood cell. You could have an A antigen, so it's an A marker or flag. You could have a B antigen or flag, or you could have what they call the RH antigen. Okay. And you got both. You could have all three. You could have A, B, and RH. That would make you AB positive. Okay. So the positive negative comes from the RH antigen. If you don't have the RH antigen on the surface of your red blood cells, you're RH negative. If you do have the RH antigen on the surface of your red blood cells, you're RH positive. Now, again, an antigen is going to be related to the production of antibodies. So let's get away from RH for a second and just look at the A blood type. So an A blood type has A antigens on its surface, no B's, only A antigens. So it's going to produce antibodies that are called anti-B antibodies. Anti-B antibodies are produced by A antigens. Okay, so people with blood type A produce anti-B antibodies, and these antibodies are then in the plasma of the blood. B blood type produces anti-A antibodies. Okay, so B blood type is against A, right? And A blood type is against B. Okay, so just keep that in mind. A produces anti-B antibodies. B produces anti-A antibodies. If I combine their blood, it's going to cause a coagulation or a clumping to occur. Okay. If I have AB blood, I have both antigens on the surface of my red blood cells. If I have O blood, I have neither. No antigens. So we'll look at that's what O really technically means, zero. O blood type. They don't call it zero blood type though. O means no antigens on the surface. So we'll talk about that in more detail in just a few minutes. But I did want to show you kind of the map. So you guys have all heard of this, right? You've heard of A, B, O, or A, B, AB, and O blood type. You've heard of positive and negative. So A positive, A negative, B positive, B negative, and so on. So this is kind of cool. It has African Americans, Asian Americans, Caucasian Americans, and Latina Americans. Okay. So A negative blood types, these are percentages, right? This is a percentage. So percentage, so African Americans, 47% of African Americans have O positive. Okay. 39% of Asian Americans are O positive. 37% of Caucasian Americans are O positive, and 53% of Latina Americans are O positive. Kind of cool. 53, 40, 37, 39, 47. Now, African Americans, lowest one, AB negative, 0.3. Asian American, AB negative, 0.1. Caucasian American, AB negative. Latina American, 0.2. AB negative, across the board, lowest percentage blood type. Okay. O positive, across the boards, most common blood type. Okay, so keep that in mind. So maybe put that in your, so O positive, most common blood type for all races. Well, at least of African American, Asian American, Caucasian American, Latina American. Okay. O positives, 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 positives. So let's just look at the positives. I always love looking at the positives anyway, of everything. So anyway, look at the positives, 24, 18, 4, 47. So that's 51, 69, 93. So 93% of African Americans are a positive Rh factor. 27, 51, 58, plus 39. So 57 plus 40, 97% of Asian Americans Rh positive. See, 33 plus 9, 42, 45 plus 37, 82. So 82 Caucasian Americans are positive. Latina Americans, 29 and 9, 38, 40, 93 positive. So African American, Asian American, Latina Americans have very high percentage of being positive Rh factors. Caucasian Americans, still high percent, 80, I don't know what it was, 83 or 87%, 82%. So, but anyhow, notice the negatives, the Rh negatives, okay, higher numbers of negative Rh factors with Caucasian American. I don't know what it means. I don't know what any of it means, really. There's been research, I do know this about blood type. Okay, I know quite a bit about blood type, but I know this about recent blood typing. They're finding links with COVID. First of all, COVID infection rates seem to be lower amongst O positive people. O positives who do get infected seem to recover a lot faster. So I don't know what it means. blood typing and eating. There are a couple of pretty big, long standing kind of research programs that have been going on for a long time on analyzing different foods and blood typing. So they say that certain blood types should focus more on certain types of foods than maybe a different blood type. So anyway, blood typing. Ultimately, on a clinical level, we're most concerned about transfusing blood and not transfusing the wrong kind of blood into the wrong blood type person. So anyway, those are just some FYI kind of demographics on blood typing. Again, O positive, most prevalent, AB negative, least prevalent. There's something called erythroblastosis fetalis that can occur. Here's another spot clinically where blood typing could matter. So if mom is a negative blood type, so mom doesn't have Rh factor antigen, dad does. Okay. Um, is baby going to have dad's blood type or mom's blood type? Don't know. It's going to be one or the other, right? Well, if baby takes on dad's blood type, baby's Rh positive, fetus baby is Rh positive, mom's Rh negative, well, that could probably no big deal. First baby, okay, because mom's blood and baby's blood, there's some specialized boundaries and barriers. We have what's called the maternal pool blood, and then we have a placental venule. So anyway, my point is, baby's blood and mom's blood in the womb, they obviously are connected, but there are some specialized mechanisms that don't allow for certain things to pass that placental barrier. So with first baby being Rh positive inside of mom who's Rh negative, we're probably not going to see much going on. But as soon as baby's born, so during birth, we're going to see the tearing of the placenta from the uterine wall. We're going to see baby's blood and mom's blood mixing more than ever. And so primarily baby's blood. So Rh positive baby blood's going to go inside of mommy, and primarily again at that where the chorion is kind of like that. It's like the amniotic sac that the baby's in, and the chorion, it all pulls apart, opens up. Everything's now exposed. Okay. So mom's going to produce anti-Rh antibodies. So she's going to be ready for an attack on an Rh positive blood again. What do antibodies do? In essence, the antibody, it's like it's almost like a staff, and at each end of the staff, there's going to be kind of like little hooks, if you will, for instance. And so an Rh antibody chemical might look like this. And so when I put this inside of someone's blood who has Rh antigens on the surface of their cells, these little hooks will hook onto those antigens, and it'll cause the blood to clump. Okay. So remember, mom's now producing antibodies against Rh positive. Okay. So second fetus is Rh positive as well. Well, now mom has antibodies against Rh blood. And they're small enough to cross through now the embryonic chorion and attack the fetus. And that can cause the fetal blood to clump or clot, and then the baby dies. So mom gets what we call a ROGAM shot, maybe even a series of them. Okay, so first nowadays, even on first babies, they'll give mom the ROGAM shot, but definitely subsequent births, RHOGAM, I think is how ROGAM is spelled. Okay. So anyhow, that's what's going on with mom and dad. So mom's Rh negative, dad's Rh positive. That could create a problem, possibly. But remember, when we look at our negatives, very few percentage of Rh negatives out there, high percentage of Rh positives, but it can still happen. When we do blood sampling in class, what we have is we're going to put 3 blood drops on 3 different little squares. We could do it on a microscope slide. You can do it just on a piece of paper, specialized, a little thicker piece of paper, but the notebook paper. But anyway, we give you a little card and you put 3 drops of blood on it. And then you're going to take what's called an anti-A serum and dribble it on one, an anti-B serum on the other, and an anti-D, which means RH, on the other one. If we get clumping is bad. This is not what we want to see in the clinic, right? I don't want to put blood in you that's going to start clumping. I want to put blood in you that looks like this. So anyway, we look at this blood sample. Let's start at the Rh factor and work our way to the left. Well, right away we see clumping. So this is positive for clumping. So this person is Rh positive. So I put their blood on the slide, and then I put that Rh anti-Rh antibodies on there, squirt, and lo and behold, we get clotting and clumping. So this is what would happen to baby if we didn't give mom the ROGAM shot. Second baby. Baby's blood would look like this instead of looking like this. Okay, so mom produced antibodies against Rh antigens. So this is what a positive Rh factor blood is going to look like. And again, when we do blood typing in class, almost everybody looks like this. All right. Now these two are a crapshoot. We never know. So we check, do they have A antigens on the surface, B antigens on the surface, neither or both? Well, this is going to be one or the other, first of all, right? You can deduce that if this was O blood type, there would be no clumping because O has no antigens on the surface. So we can't get clumping if there are no antigens. So O blood type would show both anti-A and anti-B exposure would look like this. There would be nothing would happen. That's why O is what we call the universal donor. O can give to anybody because their blood doesn't have any antibodies. They don't have antigens. You're not going to get clumping. So we know this person is not O. All right. Well, we also know they're not AB because if they were AB, both would have clumping because AB, remember, has both anti-A and anti-B possibilities. They have antigen A and antigen B on their surface. So if I give you anti-A, that's going to clump with the B antigens. Okay. So AB blood will be clumping the whole way. O blood, no clumping the whole way. I guess both way. We're just doing the A and the B. So no clumping is O. O, 0, no. Okay. AB is double clump. So now this is where it gets tricky. So what are these? Well, if you read down here, it tells you the answer, but anti-B means pro-A. No clumping, so this is A blood. Anti-A means pro-B. So pro-B clumped. If I put B with A, it's going to clump. So we know this person is A positive. Okay. And again, if this is confusing, it's understandable. We do this together as a group in class, and you'll do it as a group in some of your nursing classes. So anyhow, that's pretty much all I have for today. This is a little bit of a table that's also from chapter 18, shows the shapes of the antigens. You've got the A antigens, kind of a globy. The B antigens, they represent them as diamonds. The AB has both A antigens and B, and O doesn't have any. Okay, so O can produce anti-A and anti-B antibodies in their plasma because it's not going to attach or clump to anything. Okay, AB doesn't have any antibodies in their plasma. That's good. Okay. So AB is the universal recipient. So AB can get anybody's blood. So I could put this blood in AB and it's not going to clump because it's got the, or it has the anti-B antigen, or it has the A antigens. So I can give it anti-A or anti-B, both. They kind of cancel each other out. So AB is what we call the universal recipient. So I can put any of these antibodies in an AB blood type. Nothing's going to happen. Okay. So anyway, O universal donor, AB universal recipient. That's really all you need to know about blood typing for now. Okay. All right. Well, that's it for today. I'm going to stop recording and then I'm going to ask you guys if you have any questions.